In this first lecture, we're going to look at the ideal gas law and look at what we might already know about pressure and energy. We should already know about things like the basic states of matter. There are solids, liquids, and gases, but we'll mostly focus on gases for now. But going through thermodynamics, it will be useful to remember that changes between these states are thermodynamic transitions and have energy changes associated with them. You should also have some grasp of what pressure is and what it means. We're mostly aware of it being like a force spread over an area. Force also appears in the second law of motion, which links it to the movement of molecules. So movement, pressure, and speed can all be related, although not necessarily very simply. So by the end of this section, you should know more about the components of the ideal gas law and how to relate those properties together. This may be a revision for some of you with a light science or chemical background, but we're going to unpack and explore these terms again anyway. So, what is pressure? Pressure, as we measure it, comes from the collisions that molecules have with their containers and also with each other. If there are more collisions, the pressure is higher. So if we pump in more molecules into some space, then there are more collisions. More forces applied per area, and so the pressure is higher. The rest of this first part of thermodynamics will look at what this force can do. Now, dimensionally, there's a connection here with energy. Pressure multiplied by volume will get energy, and pressure multiplied by area gets force. There's a difference of only one length dimension there, and force and energy are then connected by that length because dividing energy by a length gets force. Anyway, this is actually reflected in the ideal gas equation, as both sides of it, as usually presented, are equal to energy. So next we're going to look at temperature. What is temperature? Well, it turns out that's a little more complicated than you might think. It's got a number of definitions, and some almost sound circular, like how temperature is a measure of the hotness of something. It also pops up later in statistical thermodynamics, where it's interpretations about how particles are distributed around different energy states. But for our purposes right now, we're interested in temperature as a function of speed or velocity of the particles. Therefore, it is a measure of average kinetic energy. Now, finally, volume. You might think there isn't much interesting to say about volume, and mostly you'd be right. Volume is just a three-dimensional space, x times z times y, or length, breadth, and depth. But everything we'll be talking about with ideal gases can actually be made two-dimensional. When we talk about surface tension, we're dealing with areas, and rather usefully, there is an ideal gas analog in 2 dimensions. This can describe things like surfactants or other materials that interact on the surface of a liquid. Now, we're not going to cover this, but it's interesting to know it's there should you do any material science later on. Now, if we combine all those things together, pressure, temperature, volume, we end up with the ideal gas law. This tells us that pressure times volume divided by temperature should always be a constant value. And that constant is related to the number of molecules in the sample. If we measure that number in moles, as chemists do, then it's the number of moles multiplied by the universal gas constant. If we're talking about individual molecules, then it's multiplied by the Boltzmann constant. So you can easily tell if an equation is talking about moles or molecules by whether it uses K or R. So if we fix one of those 3 variables, the temperature, pressure, or the volume, the other 2 will always be proportionally related. This is what the technical detail of thermodynamics is based around. What conditions are we working in? Is the temperature the one that's fixed? Are we fixing a volume and trapping everything inside a container? Are we fixing the pressure by leaving everything open to the atmosphere so it can expand? So that is the basics of the ideal gas law. Next, we'll be moving on to what happens if we mix different gases together.